Right. Good morning, everyone. Any questions? Any question before we start? So today we're going to go back to the idea of work. And as I said yesterday, we're going to do part of it now before the exam, and the other part we finish it after the exam, which is actually the hardest part. So let us recall from yesterday what we did, what we said. We said the following. If you have an object which is moving along an axis, and to move it, we need a force to move this object. And the force will depend on the position of the object. That's really the idea. So we have to move this object, and the position, the force we need to push it every time, depend on where the object is. So the force is actually changing. So f of x is the force that moves the object at the point x. Then the work done on the object, so if you want to move it from A to B, then the work done is given by the integral from A to B of f of x dx, f of x being the force, dx was the little bit of displacement that we did for the force. Okay, so that's what we did yesterday. And then we started talking about the idea of a spring. So, and today we're going to work with the spring. So work done on a spring. So we have a spring, and as we said yesterday, when you start moving the spring, the force you need to displace the spring is actually changing. The more you stretch the spring, the more force you have to do, because the restoring force of the spring always wants the spring to go back to its natural state. So the more you push, the more force you need. Now, we need a formula for the force. It means what's the formula that governs the spring? So there is a law called Hooke's law that tells me the following. Suppose you have a spring, then the force required to maintain a spring stretched or compressed x unit beyond its natural length is given by the following formula, f of x equal k times x. So sometimes we say the force is proportional to the amount of stretching. So f of x equal k times x, it means I give you the formula. So it's not x squared, it's not x cubed, it's just k times x. X is the amount of stretching. K is a constant that we give it a name and we call the spring constant. So it represents the stiffness of the spring. The more stiff the spring is to push, to stretch, the higher the value of K is. Okay, so this is our setup. We have a spring. So that's a spring. Okay, and that's in its natural state. So that's the spring before we stretch it. So that's in its natural state. Okay. The zero always, when we are working with those problems, we need an axis. And in the spring, the zero is always the equilibrium situation of the spring. So zero represents always the equilibrium position. So zero is always the equilibrium. Position of spring. Okay, so that's now we stretch the spring. So now we're gonna stretch it. So this is zero. That's its equilibrium position. And now we stretch it. So x is the amount of stretching. It means how much we move it beyond the equilibrium position. So that's the stretch spring. And x is, as I said, I emphasize this, is only amount of stretching. It has nothing to do with how long the initial spring, so it doesn't have to do anything with the natural length. It's just how much we're stretching the spring. So when we stretch it, Okay, so I stretch it. I'm going to hold it here. To hold it, I need a force. And the force is proportional to how much I stretch. K times X. So that's the picture for the spring. So now we're going to start working on a problem concerning the spring. So here is the problem. Sorry. All right. So we have a spring. So I'm going to write the problem with you. So we have the following. We have a spring. And we're going to stretch it. So example. Okay. Let us suppose it takes a force of 10 Newton to stretch a spring 0.2 meter from the equilibrium position. Okay. Question number 1 is, so number A is, find a formula for f of x. It means f of x. It means the force needed to stretch the spring x unit. The force needed to stretch the spring or compress, stretch x unit beyond equilibrium. Okay. So question number 1. So we have a spring. Okay. That's the spring. That's the 0. And we stretch it. So we take it and the stretch. So 0 is its equilibrium position. It stops like that, for example. And here's that tell me. It takes a force of 10 Newton to stretch 0.2. So if I stretch it 0.2 meters, so I stretch it that much, I want to hold it. What the force I need here is 10 Newton. That's what's given. And the question is, okay, what if you stretch it 0.3, 0.4, 0.5? So you stretch it more. What's the formula for the force? Now, Hooke's law tells me the following, that there is an easy relationship between the force and the amount of stretching. So the force is always a certain constant K times X. So there is this easy relationship between them. And now we need to find K to be able to find the force to stretch it any amount we want. So we need to find K. So what is given to us? What's given to us, it tells me that if you stretch it by 0.2, F at 0.2, you need 10 Newton. That's really what's given to us. So we're going to use this to find K. Okay, so it's basically a very simple scenario. So here, 10 Newton is the force to stretch it 0.2. That's really 10 Newton. So now I say, okay, the relationship is easy. So this tells me that K times 0.2 is equal to 10. This will help me to find the K. It's 10 over 0.2, which is 50. Means that the force is given now by the following formula, 50x. So now if I stretch it by 0.3, I need 50 times 0.3 Newton force. If I stretch by 0.5, 50 times 0.5, and so on and so forth. So now I have a simple formula for the force. So anytime I want, so now I'm back to my original scenario. I have an object, which is the spring, and this object is moving. So you can imagine, concentrate on the mass attached to the spring, and this is going to be moving. As it moves, the force need to move it is given by this formula. So now question B is going to be work. So question is, find the work. The work done to stretch the spring let us say 0.5 meter from its equilibrium. Okay, so find the work needed to stretch down on the spring, down to stretch the spring 0.5 meter from its equilibrium. Okay, so now this is my spring. I'm gonna stretch it from here, 0.5 from equilibrium. Me is my spring. I wanna stretch it from here all the way to here. So that's really my spring. I need to stretch it from here to here. What's the work done? Now I know the force needed at every time. I know the force needed. So the work is equal to the integral of the force, 50x. I want to move it from the equilibrium to 0.5. So this is my A and B. So integral from 0 to 0.5 of 50x dx. And now the rest is simple. 50 is a constant. I can take it out. Now I'll be left with the integral of x dx from 0 to 0.5. It means it's 50 times antiderivative of that is a half x squared. Now I can pull out a half, which is going to give me 25x squared from 0 to 0.5. And then I evaluate. I get 0.5 squared minus 0. And then as I pick up my calculator and I get 25 times 0.05 square, I get 6.25. And now the unit is the unit. I use meter and Newton. If I use meter and Newton, the unit is just joule. Okay. All right. Let's do 2 more questions with the same problem and then we move on. So part 2 is find the work needed to stretch the spring. Let us say from 0.2 meter to 0.5 meter. Okay, so this time my picture is like this. This is my 0. My spring is at 0.2. So my spring is here. Now I'm going to stretch it till 0.5. So I'm going to stretch it from here all the way to here. Okay, so we're going to stretch it. So we're going to move it, stretch it. And what is the work? Again, this idea is fairly simple. In this case, it's the integral from 0.2 to 0.5 of the force, which is 50x dx. And then we compute that, and that's going to give me 25. If you do that, x squared between 0.2 and 0.5. And we evaluate, and we get 25 times 0.5 squared minus 0.2 squared. Okay, and I think computing this is actually shouldn't be hard. It's just pick up a calculator and proceed. It's going to give me times 25 and then 0.21 times 25. I'm getting 5.25 joule. Right. The last question concerning this problem is the following. What if we compress the spring instead of stretching it? What will be the formula? So the question is, how much work is required to compress the spring? It's the same spring. We're not changing anything. 0.2 meter from its equilibrium. Okay. So how much work is required to compress it? All right. So the idea here is this is my spring, that's the equilibrium here. Okay. And one easy way to think about compression is basically think about, since to compress, we have to exert a force going to the left in this problem, just orient your axis so positive go to the left. So now this is my spring, we're gonna compress it, 0.2. So we're gonna move it from 0 all the way to 0.2. So my spring was here, we're gonna compress it all the way to here. So the work is going to be, so one easy way, as I said, because the force is going to the left because we're compressing. So I'm gonna orient my axis positive going to the left. And the process will be the same. So the work is going to be now, nothing changes, from 0 to 0.2 of 50x dx. So it will be exactly the same thing. You can think about exactly the same, but you change the orientation so the problem would work. Okay, so and then we evaluate this quantity, and so I did, okay, have we done something like that? So that's going to give me 25x squared from 0 to 0.2, which is, I think we've done it a minute ago. No, I didn't. So this will end up giving me 25 times 0.2 squared, which is going to give me 1 joule. All right. So the problem of spring is not actually hard. The work done on a spring is not hard because we can find the force easily. Either once I have one piece of information, I can find the force actually very easy. All right, so we're gonna do now another problem with, yes.
So will our answer always be positive?
Yes, that's why I changed the orientation. Yeah, at least in this course, whereas we're taking work always positive. In physics, you guys will study negative work, but not in this course. Okay,
thank you.
Yeah. It's a different scenario. The work is negative, the scenario has to change a little bit. Right. Now we're gonna do another problem, which is basically preparation for your MATLAB and for your exam. Example number 2, along the same line, I'm not changing, it's also work. And this is my problem. If the work required to stretch a spring 1 foot beyond its equilibrium is 12 foot-pounds. So that's the work. And how much work is needed to stretch it 0.75 feet beyond its natural length. So let me first go over the first problem, just to make sure we get it. In the first problem, what did I give you? I give you the spring, and I told you the force you need to stretch it to a certain given length. Now we use this information, we use that information and Hooke's law to be able to find the constant K in the first problem. Once we find K, we can find work. Become very easy. Okay, so if I have one piece of information, it's very easy to find work. Now, so knowing the force is crucial in all those problems. So now I'm having a little bit of a twist in this question, which is my following. The work required to stretch a spring 1 foot beyond its equilibrium is 12 foot-pounds. How much work is needed to stretch it 0.75 feet beyond its natural length? The main idea to find, so we need to find the work. That's what we need to find. We need to find the work to stretch it. But to be able to find the work in the spring, we need a formula for the spring. The question is, I let you interact with it a few minutes. How can we find a formula for the spring in this problem? Okay, I want you to think about it a little bit and see what, read it so you can interact with it and think a little bit about it.
Maybe we could find the pounds, start by finding the pounds. So maybe we could divide 12 by 0.75.
12 is the work needed to stretch it 1 foot is 12 feet. That's the work. How much work is needed to stretch it? 0.75. So I'll start by giving you a hint. Okay, we need to find, we have to find f of x, the force. So to be able to deal with work, we need to find the force. Times x, okay? And did they give us information to find the force? In the previous problem, the information was that if you stretch it by 0.2, you need 10 Newton. That was the information. And we used that to find the K. Okay, so I can give you a million along the same line, but it will be boring. So now I switch it a little bit. I did not give you information about the force, but I gave you something. How can I use this information to be able to find the K?
Is it 12 divided by 1? So your force divided by your distance that you're going to stretch it?
Read the problem again. What does this 12 represent?
Your force, so
No.
Foot-pounds.
What does foot-pound is unit of what?
Work.
It's unit of work. Pound is a unit of work. So it's not a force anymore. Okay, it's different from the previous problem. The previous problem, I gave you the work to stretch. Sorry, I gave you the force to stretch. This problem, I did not give you the force to stretch 1 foot. I gave you the work. How can we use this information to find the K? Basically, that's what I'm going to be after.
Would you say that 12 equals the integral from 0 to 1 of k of x dx and then solve for k?
It's absolutely correct. Let's repeat exactly what your classmate said. She said that the work to stretch, I'm going to rewrite this, the work to stretch. So question, we need to find K. So the work to stretch, so you have to read the problem very carefully. Are they giving you the force to stretch or the work to stretch? So are they giving, in this case, I'm not giving you the force because I've already done it in the previous problem. I'm giving you the work. So the work to stretch 1 foot is, how much? Is 12 foot-pound. That's the work. So how can I use this information to find K? So now I say, okay, what's the formula for the work? The work is the integral from 0 to 1 of kx dx is equal to 12. Okay, so here this is 12 foot-pound. So to find the work, we need a formula for the force. How are we going to find the formula for the force? I go back and read the problem. They should have enough info to do that. So in this particular problem, the information was that the work to stretch 1 foot is that much. So now I can just find K. So this is going to give me K is a constant. I can pull it out. And this will give me the integral from 0 to 1 of x dx is equal to 12. And that will give me K times a half x squared between 0 and 1 equal to 12. It means K times a half equal to 12. It means the K is equal to 24. Okay, so this time, because the work is given, and the work is given by the integral, it's not a force. So this is going to give me that K is equal to 24. So now I have a formula for the force. So the force is 24x. So it's really be about reading the problem very, very carefully before proceeding. So now the question is, how much work is needed to stretch it 0.75 foot beyond this equilibrium? So now work to stretch it 0.75. Is equal to the integral from 0 to 0.75 of 24x dx. Now, there is nothing left into it, so that's 24 times a half x squared between 0 and 0.75.
Professor,
I'm stopping.
does it matter that the problem says it's beyond the 1? So wouldn't the bounds be 1 and 1.75?
No, because I said beyond its natural length.
Oh, okay.
Okay, otherwise you would be right. If I said between 75 and 1, yes, but it's beyond its natural length. Okay?
Thank you.
Sure. So it's going to be equal to a half could be factored out, give me a 12.75 squared, and then the rest is just computing. So it's going to give me 12 times 0.75 squared, which is going to give me 6.75, and this time the unit are foot pound. All right, so two simple problems that deal with spring. In the first problem, I gave you information about the force, and we used it to find a general formula for the force. And this problem, I just gave you information about work, and I asked you to find, you use it to find information about formula for the force. Once I know the force, finding work for spring is actually nothing really to it. It's just a matter of taking it into. Any questions? Okay. Now, if we're going to do one problem, which is the problem is not spring, because the spring, that's what we did, is about it. The problem is about the leaky bucket. It's like a bucket that, as you're lifting it, is just leak. And the question is, find the work needed. But before I do that, I'm going to talk a little bit about unit. So more about the unit. Unit of weight, of force, actually. Okay. Now, the two units of force that we have, that we know is, the two units of force we have is a pound and a Newton. Okay. Now, what about kilogram? Is kilogram a unit of force? Back to you. You guys remember? Anybody has any members about kilogram? Okay, so let me remind you. Let us recall one thing, that kilogram is not a unit of force. Kilogram is a unit of mass, not a unit of force. Meaning, if you take an object in kilogram, if it weighs 5 kilograms on Earth, it will definitely weigh 5 kilograms on the moon. That's right. So it's a unit of mass, not a unit of force. Of force. Only pound and newton are unit of force. So if you are working with a work problem, it doesn't have to be spring. We're going to do other problems. If you're working with work problem and the unit is in mass, you have to convert it to a unit of given. So when the mass is given, then the force needed to lift the object is given as follows. So if you have a mass and you want to make it into a unit of force given by the following, it's the mass times g. G is being the constant of gravity, where g is 9.8 meter per second square. Okay, so if a mass is in kilogram, F is in Newton. Okay, so let us a little bit repeat. If you're working with a problem and they give you the mass of the object and they give it to you in kilogram, kilogram is not a unit of force, it's just a unit of mass. So most of the time you have to convert it, if you want, to become a unit of force. To do that, you multiply m by the constant of gravity, which is 9.8. And the resulting is given in Newton. So the Newton is the weight to lift 1 kilogram, is the force, needed to lift 1 kilogram. That's what Newton is about. So for example, so very simple. Suppose you have the following example, very simple example. Find the work required to lift a 2 kilogram stone above ground level. Okay. 3 feet. Okay, 3 meters above ground level. All right. So here, no, I'm not dealing with slugs. In this class, we only deal with that. Okay, and mainly kilogram. All right, so find the work required to lift a 2 kilogram stone 3 meters above ground level. All right, so this is really the question. So basically, that's a constant force. So we have this stone here. We're gonna lift it 3 meters. So it's a constant force. There is no problem about it. So the work is nothing more than the force times the distance. Okay. So in this case, my distance is 3 meters. But what is my force? Since I'm giving you the mass of the object, it's going to be 2 times 9.8. That's going to be the force. And times the distance, which is in meter. So which is going to give me 3 times, I don't know. So let's do that. So it's going to be 2 times 9.8 times 3, which is 58.8. So this is going to be 58.8 joule. Okay, so if you're working with a problem, I don't know if this book has problems with kilograms, but if you are working with kilograms, then it's only a unit of mass. So you cannot use it to represent the force. You have actually to multiply it by 9.8, so it will become a unit of force. One is a unit of force, you multiply it by distance, and then we're back to our original problem. Okay. Is it supposed to be joule or Newton? The force is Newton. The force is Newton. The work is joule. Am I answering a question? Yeah. The force is in Newton, the work is joule. Very good. So now I'm going to take a problem but this one I want you to think a little bit about it because it's not very simple as to spring. You practice spring for tomorrow. Yeah, 9.8 is the gravity, yes. 9.8 is the constant of gravity. Yeah. So I'm going to set up the problem. I'm going to let you think a little bit about it because it's not as simple as the other one. And we finalize. So the problem of what we call the leaky bucket. Actually, it's a problem taken straight out of your book, one of your homework. Okay, a 1 kilogram bucket resting on the ground contains 3 kilograms of water. How much work is required to raise the bucket vertically a distance of 10 meters if the water leaks out of the bucket at a constant rate of 1/5 kilogram per meter? Okay, I want you to read the problem again and think about it. So this is 10 meters from here to here. This is my 10 meter. And I have this bucket and I am lifting it. Now you can imagine we're lifting it by a rope, but the rope doesn't weigh much. So we're neglecting the rope because the rope is problematic and that's something we will take on after the exam. So imagine now we're just basically lifting it. And as we lift it, it's leaking water. It's leaking water. So its weight is actually decreasing or it's changing. So the question is, how can we find the work? Read it a little bit, interact with it, and then we start talking about it. Any ideas?
Can we somehow find the equation of the curve of like what that represents of it losing water every meter?
Repeat. So I can explain what you're saying. Repeat.
Is there a way that we can figure out what that curve, what the equation of that curve is of
What curve?
of the bucket losing water?
So the equation
Well-
of what? Try to be precise.
So the distance of where the bucket is at compared to how much water is in it at that distance, and what that curve looks like, or that equation.
Yeah, so
That
there is
equation.
no curve, but let me try to explain what you said. So suppose the curve is, so let me call this y-axis, because we call it the y-axis, okay? And this bucket, you are lifting it. And as you're lifting, so if the bucket is here versus the bucket is here, definitely the force is changing. So the question is, can I find equation not for the curve? Can I find equation for the force needed to lift the bucket once the bucket is y meter above ground? Okay, because in the previous problem, to be able to solve this problem, most of the time I took the motion to be horizontal, but it doesn't really have to. What we need to know exactly is that once it is in a position X, what's the force needed to push it a little bit more? Now I'm going to do the same. Suppose the bucket is here. What's the force I need to keep lifting it? And the force I needed is basically the weight of the force. So suppose the bucket is at the point Y. Y above the ground. And let F of Y be the weight of the bucket, because that's the force you need to lift it. Weight of the bucket at the point Y. Okay. And the question is, can we find a formula for F of Y? Okay, so imagine, so now the object which is moving for us is this bucket. That's really the object that's being moving. And to be able to find the work, I have to ask myself, okay, when this bucket is here, what is the force need to lift the bucket? The force need is actually the weight of it. So now the question is addressed to you. If the bucket is here, what's the weight need to lift it? Now this is the given. I want you again to think about it. All of you. And you guys are all hiding your faces today. Yeah, anybody else?
Wouldn't it be 4 minus x over 5?
4 minus x over 5. Are
That's
you
times
guys-
9.8.
Yeah, you guys agree with them. Let's see where they get the 4 minus x over 5 from, or y over 5. The bucket by itself weighs 1 kilogram. So that's the bucket, empty bucket.
Okay, that makes sense.
Okay, that's the empty bucket, right? And then there is water in it. Okay, 3 kilograms of water inside it. But then it's leaking. And how much it is leaking? 1/5 of a kilogram per meter. Okay, so it's leaking. So it's 3 kilogram originally, but it leaks. So it's losing weight. It's losing 1/5 per meter. So if it's gonna go Y meter, it's gonna lose 1/5 of Y. Okay, so that's really what's going to be the force. So this is the empty bucket, and this is, if you want, the initial amount of water in the bucket, you're taking away how much it leaks. It leaked 1/5 per meter. It means if you lift it Y meter, it's gonna leak basically 1/5 of Y. So that's water, that's the empty bucket, and that's the water when the bucket is Y meter above ground. Okay, so the total weight of the bucket is going to be 4 minus 1/5 times Y. Okay, so that's really the force. So that's a typical example of a variable force, which is easy for us to understand. So it doesn't require so much physics in those problems. I leave your physics professor to explain, to give you hard problems. So now what's the total work? So now once I found the force here.
Professor, isn't that the mass of the bucket?
That's the mass, and thank you very much. And that's why I made a whole lecture about mass. So that's the mass of the bucket. So now the weight of the bucket, or the force, the weight of the bucket, thank you very much. And I made sure to give you a lecture about it before this problem. So weight of the bucket is 4 minus, or that's the force basically, times 9.8, force due to gravity. And now finally, we need the work. Now I have the force at every height as my object is moving. So finally, I need the work. I need to do that. So if I want to lift it from ground level all the way to 10 meters, now the problem usually is this is attached to a rope and we're using the rope to lift it. But the rope in this particular problem, I'm assuming the weight is very negligible. So I don't want the rope to get into the way because that's what I have to work with later on. So now the work is integral from 0 to 10 of 4 minus 1 over 5y times 9.8 dy. Okay, and now it's a matter of computing the work. So we multiply by 9.8 because I gave you everything in kilograms. So that's kilograms. You multiply it by 9.8, which is meter per second square. And the unit here will be the Newton. So that's really the unit. So the Newton is 1 kilo, the weight of 1 kilogram. So now finally we have to integrate. The 9.8 is my constant. You can take it out. And this will give me dy. So finally I will get 9.8 times antiderivative of 4, it's 4y. Antiderivative of 1 over 5, that's going to give me y squared over 2. Evaluated between 0 and 10. And then the rest is, so it's a 10 minus, I meant 40, minus I will have 100 minus 10, which is going to give me 9.8 times 30, which is going to give me a 4, and give me 29, and it's give me 29.4, which is, and the unit this time, it's in joule. Okay. Okay, any questions?
So all we had to do to convert it from mass to weight or force, I guess, is just multiply by 9.8.
Exactly. Yes. Yes. Yeah. Otherwise, it's not a unit of force. It means, as I said, if something weighed 5 kilograms, this is what it's made out of, basically. So that's the weight here on the moon, everywhere. It doesn't take gravity into consideration. But the force takes gravity, because when you carry an object, you're basically fighting the gravity itself. So the force is not only 5, it's 5 times 9.8, because you have to compensate for the pull of the gravity.
I have a question.
Yes.
So what you did with the 9.8 was you just multiplied it after you had finished with the integrals.
No.
Could we do it like while we multiply kind of while we put in the
Here?
no, I'm saying like right where you have the integral, where you create the integral from 0 to 10.
Yes.
Could you simply just like set each integral as 9 times 4 for y minus 110 y squared, and then just substitute the numbers for y?
But this make it harder. Why would I do that?
Oh, I mean, if you can.
Yeah.
I mean,
yeah.
I'm just so used to doing it. So
No, because it's a constant. I would rather take this constant and factor it out. The math will be easier, way easier. I hope I'm answering your question.
no, okay.
Yeah.
All right, thank you.
Much easier, because why you want me to multiply here and have to, instead of dealing with 4y, I will be dealing with 4 times 9.8 times y. Why would I want to do that? That will be much harder. I just factor it out as a constant, and I will deal with an easier integral. That's what it is. Okay.
All right, thank you.
Any other questions? Okay, so I will stop here today. Tomorrow when we come after the exam, we have other work problem. Usually they are harder than those, but that's why I left them for after the exam. And tomorrow I will review the exam with you. So please do your homework, your MATLAB homework, do it tonight. Don't wait till Friday so you use how to do spring problem, because spring problem are going to be on your exam. So don't wait till after the exam to do the MATLAB, and then you will lose on the spring problem on the exam. Is that very clear? I mean, losing 10 points on the exam is losing 10 points. You're done. I mean, it hurts you. So please, the MATLAB problem assigned for tomorrow are about the spring. Please do them. They are easy. Actually, I did most of them in class today. So you'll be all right. So do those, and I hope you're doing the review, and tomorrow I will review everything with you, anything you have. And as you guys know, the exam will start at 7:30. Does any student has any objection with that? Any student have any objection with the exam? Okay, if nobody have, then great. So good luck, and I have office hours now. If anybody has question, please join me. Bye-bye.
Are we going to be in the Zoom lecture by 7:30? Is that what you want us to do? Okay.
Yes, yeah. And I really would like your camera on. I hate to keep pushing you, but I would like to have your camera on. Okay? Bye-bye,
Have a good
guys.
day.